Hello everyone, this is Koteshwar from IIIT Delhi presenting our work titled A Vision-Based Solution for Track Misalignment Detection. We consider two types of misalignments, lateral and vertical. Lateral misalignment can happen due to buckling phenomena where a longitudinal compressive stress develops due to difference in temperature from what is considered normal. The vertical misalignments can happen due to hogging. In hogging, the ends of the railway tracks where they join, there a bend happens, as you can see in this figure. And when railway wheels pass on such bends, that causes a small jump for them. And when they land on the remaining portions of the railway tracks, further jumps, further dips happen, and which leads into vertical misalignments. So to detect these visually, we collect several images from internet comprising of these defects and also few normal ones. And this is the data set we have, and we collect about 555 images, and around 20% images were dedicated for testing purpose. In the transfer learning approach which we take based on these images, we have two sets of two hyperparameters. One is the pre-trained network itself we use for feature extraction, and the learning algorithm we use for learning the model. Now, we have options for these hyperparameters. As we tune our hyperparameters over these options, we need to select the accurate, precise model. So to model the accuracy, we take into account training and validation accuracy, and we have this term which is bias-like. And more the training and validation accuracy, we get this bias error as very low. And then we have variance-like term, lesser the difference between training and validation accuracy, the term becomes very low. And these two errors need to be jointly minimized. And when we are minimizing, we have different weights for these errors, and these weights need to be in the range of 0 to 1. And when we are trying to minimize this portion doesn't play any role in minimization. And if we are trying to minimize this, it means we want to maximize the negative of this exponent, which we denote as x. And as we are trying to maximize x, if we want to have the same range as v and t, alpha, this term, this coefficient and this coefficient should sum into 1. To have their sum as 1, alpha needs to be half. And if we can get half, we can get alpha like this, but still beta remains. And beta is an application-dependent hyperparameter, because beta denotes the variance parameter, and depending on variance, wait for variance term, and depending upon the variance that exists in the images, we can set our beta. Now, x, we select those models with x having x which is greater than certain threshold, and this threshold is determined by the average and standard deviation of all the x values we got for all the models we considered. And these are the results which we get for all the models we tried out. Their training and validation accuracy is given, and their x value is given. We select 7 models based on that criteria, and we see that their test accuracies are also very high. However, we did miss few of these red ones. We say we have missed them because their accuracy is higher than average of the accuracies we get for our selected models. These are few images which got uh, classified as defective correctly, and these are images which got classified correctly as normal ones. While concluding, we would like to point out that we tried to detect misalignments, both horizontal and vertical, and then we try to identify those transfer learning models which are both accurate and precise, and we select few good ones, and out of those good ones, we found out that inception B3 plus NN was the best, as you can see from our test table. Thank you so much. If you do have any questions, please ask us.